Welcome to The Explainer. Today, we're digging into a really fascinating paper from WeChat AI and Tsinghua University. They're proposing a way to completely shatter a fundamental speed limit that has been holding back large language models for years.
All right, let's kick things off with the big question at the heart of this research. Why are even our most powerful, most sophisticated language models so incredibly slow and just plain expensive to run?
Well, the answer actually lies in this fundamental inefficiency that's been baked into their design from the very beginning. They generate text one tiny piece at a time.
So what's the culprit here? According to the paper, it all comes down to the token. You have these incredibly powerful models that are forced into this slow, laborious loop of predicting just one single, low-information piece of a word at a time. You know, the best way to picture this is like an internet connection. On the left, you've got traditional next token prediction. It's like a slow, painful dial-up connection, processing one tiny packet at a time. The solution they propose on the right is next vector prediction, and that is a fiber optic upgrade. It predicts a dense vector that represents a whole chunk of text all at once, which massively boosts efficiency.
And that's where this new paradigm shift comes in. It's called CALM, which stands for Continuous Autoregressive Language Models. And it's all about making that leap from tokens to vectors.
So what exactly is CALM? Well, at its core, it's a framework that completely changes the game by shifting the goal. Instead of asking the model to predict the next discrete token, it learns to predict the next continuous vector, where each vector represents an entire chunk of text.
It all happens in this really clever two-stage process. First, a special component called an autoencoder learns how to compress a chunk of tokens, let's say 4 of them, into one single, dense, information-rich vector. Then, the language model itself is trained to predict that vector, not the individual little tokens.
And just how good is that compression? I mean, it's practically perfect. We're talking over 99.9% accuracy when it tries to reconstruct the original tokens from that single vector. This near-lossless compression is the secret sauce that makes this whole system work.
Okay, but here's the catch, right? When you move from this world of neat, discrete tokens into this continuous space of vectors, your old tools just don't work anymore. You need a completely new toolkit.
So here's the problem in a nutshell. Standard models, they use this method called softmax to basically pick the next word from a fixed dictionary. But in this new continuous space, there is no dictionary. There are infinite possibilities. It's a massive technical hurdle to overcome.
So to tackle this, the researchers had to build a whole new toolkit from the ground up. It's got 4 key pieces: a really powerful yet lightweight autoencoder for that compression step, a whole new approach to modeling using something called an energy transformer, a new metric called BrierLM to even measure performance in this space, and even a new way to do sampling. The whole shebang.
All right, so we've got all this cool new tech. What's the payoff? What do we get out of it? Well, it's a massive boost in something the paper calls semantic bandwidth, which really just translates to huge gains in performance and efficiency.
And this introduces a really powerful new idea: semantic bandwidth, represented by the letter K. All it means is the number of tokens you cram into each vector. But what it gives model designers is a brand new dial to turn, a new way to scale things up that's just as important as model size or the amount of training data.
Now, this is where it gets really interesting and kind of counterintuitive. Look at this. When it's compressing 4 tokens at a time, the CALM model is actually larger than the baseline. But because it's thinking in these bigger, more meaningful chunks, it needs way fewer computational steps, or flops, to get the job done. It's bigger, yet it's cheaper and faster to train and run. And this chart, this really tells the whole story. You can see that when you're just compressing 1 token at a time, so k equals 1, CALM is actually not great. It's less efficient. But watch what happens as you increase that semantic bandwidth to 2 and then to 4 tokens. The efficiency just skyrockets, blowing past the traditional models. This is it. This is the core validation of their entire hypothesis. So what you should really take away from all this is that KLM isn't just some small tweak or optimization. No, this is a potential glimpse into a future that moves beyond the token entirely. And the authors, they make a really bold claim here. They say that, as we look toward the next order of magnitude in scaling, the discrete token has become a vestigial constraint. Wow, I mean, think about that. The very building block that enabled this entire AI revolution is now the main thing holding it back. And that leaves us with this final, really provocative thought. If we're no longer bound by these individual tokens, if we're not just predicting one word at a time but entire concepts,
what becomes possible? When we take the brakes off, what does that next generation of AI even look like? What will it truly be capable of?